Yeah, so welcome you all. Come back to the second day session of this particular GAN course. So yeah, Professor Sadiki will continue, and then after that, I'll take a few lectures on turbulence and things like that. So that's the plan. Okay, Professor Sadiki, it's up to you.
So thank you. I welcome everybody. So yesterday we started with atomization of jets and film. And today we will continue by seeing some properties of spray structures and nozzle type. And the first one is I think we started with the pressure atomizer. And today we will continue with pressure swirl atomizer. We have introduced both concepts yesterday. And this pressure swirl atomizer is a swirler which produce wave formation of the surface of liquid sheet. How? Here within the nozzle, so there is a production of radial acceleration of the liquid so that we can obtain more liquid spread readily upon exit. And we see that these give rise to hollow spray cone with a wide angle. Yesterday, we have seen that this angle can be can reach a value of 175 degree in this table. So pressure swirl, as you see here. So that is what we have found yesterday. And at the same time, we have a wave which is formed over the surface. So this can be reached by very less injection pressure. And the droplets here in this current is the droplet formation involve two stages. The first one, we have naturally the sheet formation with a wave on the surface, and lambda here is the wavelength. We have the first stage is, we can say, the ligament formed from sheet breakup, and further we have breakup of the ligament into droplets. And the question will be how we will find this diameter here, and this diameter is being found by this guy, Sorley, based on his theory. So the ligament and droplets diameter are shown to be a function of the length scale of the waveform of the surface in these ways. This is a DL. Here the diameter of the ligament, D is the diameter of the droplets. We will see how we can get also this D. So this is the expression, and it is the liquid sheet thickness, and we have the length, the wave length. And from experiments, we can do some sensitivity studies, how this wavelength evolve in dependency of the Weber number, and this Weber number is also an expression of the liquid injection pressure. So we see that the short wave here, the short wave are attenuated by higher Weber number. The sheet experience higher aerodynamic force in this region due to the increasing injection velocity, which is related to this higher Weber number. And we see also that the long wave are not attenuated. And we see here for two different experiences. The first one I will show you, that is the mass flow rate, 0.5 and here 1.7. So we obtain almost the same behavior. And the value of this diameter of the ligament is given here by this expression, and in this region by another expression. But if the momentum flux ratio is very high. So we see that there is a, we have, in the case we have two fluids, gas and liquid, then we have really the twin fluid atomization, in which we have a transfer of kinetic energy between the two fluids, and the transfer of kinetic energy from fast moving air to liquid cause the explosive breakup of the liquid jet. And this is called the air blast atomization we have introduced before. And here I sum up all these things. If we deal with the twin fluid atomizer, it is also in the table I gave you yesterday. We have these two options, air assist atomizer or blast atomizer. So I show you a little bit here how we did it. So we have this twin fluid, we have air assist and air blast atomizer. Everything is sum up, was shown yesterday there, and here we will like only to go to put more details. So we have a low amount of air at high velocity to create this assisting, this air assisting atomizer, because the air will have a very, very high velocity, and we can have internal mixing here. They mix internally and they come out together, and the externally. So we have the liquid and the gas and they mix here at the outside. We have almost the same here. Air blast atomizer, we have the plane jet. They mix at this point, and the premix, the pre-filming, we'll see it now here. We have a liquid and the gas, and here we have a building of a pre-filming surface, and then they decompose in small droplets. I sum up again. We have seen this yesterday, and this is what we have seen today. We have this twin fluid atomizer. We have the plane coaxial air assisted, and here we have swirl assisted. The evolution of also the diameter, we have seen the evolution of the wavelength. We have almost the same behavior here with, if we look at the evolution of this as function of the wave number. And we have also the evolution of the droplets diameter as function of the wave number. And we see here these two kind of experiment. We have the flow rate, here, and we have different orifice, 0.3 millimeter and 0.5. And we see the dependency of the orifice is not observable here. We can say that the variation of the primary ligament as function of this wave number, we have the impact of airflow scheme, but we don't have the dependency of the orifice here. For this kind, here we have also a variation. We depend on the orifice, but not really on their flow rate. And the big and important quantity is this momentum flux ratio I showed you before. And here we can see that if we focus on this pressure and pressure swirler, we can also see the difference here, what we have yesterday. And we see also that we have this difference based on the viscosity and also on the mass flow rate, but also on the injection, the injection pressure, and also on the produced droplet size. And naturally, we have also the difference on the spray cone angle. For the plane coaxial assisted air assisted atomizer, so we have the shear layer, which is formed between the liquid and the gas, and depending on this ratio, we have this distribution of droplets, and also we have these the ligament, ligament lengths, the core lengths as we have here, and we can get it experimentally. We can see it experimentally. It is the length of the breakup, and the breakup regime for such kind of atomizer, we have seen the regime breakup, the breakup regime for the jets. Here we have for this plane coaxial assisted, we have almost the same event, but in a different scaling. And here we have the web number, and we have the liquid Reynolds number. And we see that we have almost the same regime, relay breakup, non-asymmetric relay breakup. And we have here, we have the membrane breakup because we have this thin the sheet, and we have also some fiber tape recirculating gas cavity, and we have also the atomization due to the formation of this ligament. So we see also that if this ratio is very high, we have this air-blast atomizer. And this is due to what we observe here is due to the shear instability caused by the posed at the interface due to the discontinuity of the velocity, because we have this shear layer here. So the velocity of the liquid and the velocity of the gas is very high. The velocity of the liquid is not very high, and we have a discontinuity here, as discontinuity causes what we observe here. The spherical coaxial assisted atomizer, we have two phenomena. We have the swelling airflow, which is created within the nozzle, and we have the holocone liquid jet, as we have seen, and this produces what we observe. It is we can say it is a catastrophic breakup, but these swell coaxial assisted atomizer produce this kind of breakup, which feature three types of phenomena. We have a preferming, we have a piloted, and we have also plane jet air-blast atomizer effect. So we see that is here. It is a very nice. I forgot to put the reference. It is a very nice investigation carried out here in Darmstadt by the colleague Reusmann, and is a PhD student. So we have this air-blast atomizer with preferming. So this is the atomizer, and here we have this swirler. So we have the spray which come and impinge this surface, and this form a film here. That is why we call it a preferming. And due to the air which come from here, we have this sharing, which called the atomization at this position. So that is a picture from experiment. And here we see these three regime. We have the preferming, we have the air-blast spray, and we have here the primary spray, and it is assisted by this here, which really move everything in this direction. So we have a different phenomena. We have primary spray generation by pressure swell nozzle. This is what we have here. We have droplet evaporation in the atomizer. We have also secondary drop breakup. This is a primary, and we have the secondary here, which is formed. We have spray wall interaction leading to generation of secondary spray and spray deposition in prefilmer. And we have disintegration of the liquid film on the prefilmer by air flow It is very complex, and we did this carry out also some simulation of this, but we're not sure. So to show everything now numerically, the best way to do is to carry out the DNS, but the DNS of such complex configuration, of such complex phenomena is very costly. That is why at the beginning, we developed so-called embedded DNS of primary breakup. It is DNS, but we reduce it in a very, very small computational domain, and we embed it in an environment in which we calculate the boundary conditions using LES. It is, we based on the volume of fluid method, well, we have first the equation of the continuity equation and the momentum equation, in which we add the surface tension force. I think everything is clear here. It is incompressible. We have no phase transition. So the equation now, the continuity equation. For incompressible, here we understand incompressible means constant density. And we have the momentum equation, in which we have the velocity and the density. It is a gravitation force, this is the pressure. And here we have the Cauchy stress tensor, we have the viscosity here. And we have the gradient of the velocity. It is in its symmetric part. And here we have the surface tension. We have kappa is our curvature, and this is the normal unit function. And this is our surface tension coefficient. So it is related to this. So, but we need also an equation for the phase interchange transport. And for that, we include the volume of fluid method. And this is a very simple method. We try to distinguish the domain where we have liquid, domain where we have only air, and we define the volume of fraction, the volume of the liquid volume fraction, and we follow this, we track this, and we say, for example, where the liquid fraction is equal to what the volume the liquid volume fraction is equal to 1, we have only liquid, and here we have part of liquid, part of gas, and here we have also already some 10% of liquid, and we can now say that here we don't have liquid, we have so we have only gas, and we can say, okay, this part here is my interface, and I follow it based on this alpha, where we introduce also a compressibility, a compression term in this advection equation. And for that, we don't need a geometrical reconstruction of phase interface. So if we have this, we define also the surface tension. We have written as function of alpha now, and we put in our equation we had before. We put it in this equation we had before, and then we can define our surface tension and using this curvature. So then calculation, and we have the bulk velocity is 50 meters per second. We have the fuel, it is injected here, and we have we have 115 million cells. The Weber number is 21, and the Reynolds number is so fine, and the film thickness is 100 micron, and we have 20 micrometer in top, bottom, in top and here. So the computation domain is very, very small, so that we can really refine everything and carry out a correct DNS. And you can see the evolution of the film and the breakup of this film. And we can also reconstruct different steps of this breakup. We have from the big breakup to catastrophic breakup. So we published this in a paper. You can see if you have interest on this. So we did also in the past the jetting crossflow, and volume of fluid simulation of the primary atomization, and we could compare the trajectory of this jet with experimental data from Becker and from HASAP, from the Aerospace Institute here in Germany. So it was in 2009, here to show only that it is possible to also track this process of atomization using numerical simulation. We also try to calculate this jet breakup, and we use also volume of fluid method, and the experiment was from Tropea. And this is what this is experiment here, and it is what we obtain. That is the evolution of the building of instability on the surface. First, for this Reynolds number, we don't have instability from 3,000. We have it, and 3,500. We could get it. So we have seen from this configuration, this pre-film air blast with pre-filming. So we have the formation of film on the surface, and this is due to the impingement of spray on this surface. And it is a very, very interesting problem if we deal with the cooling, and if we deal also with such kind of after treatment, exhaust after treatment. For example, we have APGAS, we have exhaust from IC engine, and we would like to reduce the NOx, and for that we have we inject AdBlue, and this AdBlue evaporate fast, and pinch the wall in this channel, and we have also interaction between droplets and the wall. We have also this film evaporate, and we have also deposition of particles. And in there, if we impinge in this in perpendicular direction, so we can see such kind of processes. We have with the main wall jet region, in which we have the wall spray radius. Here we have stagnation region. We have the wall jet vortex, and also we have this wall spray head, and this is the result of this impingement between spray and the wall. But we can also have some other processes, and this, for example, has been published here. And from this calculation, we could derive another regime, breakup regime. And for that, we have different regime. We have deposition, we have rebound. We have rebound with breakup. We have boiling induced breakup, and we have also splashing. And we could obtain everything and also compare with experimental data from a group in Karlsruhe within our group here. And this region map has been plotted as a function of K and T star. And this T star is the ratio of the saturation temperature and the wall temperature. Some people also define it as the difference between this wall temperature and the boiling temperature divided by the by the temperature on the wall, by the saturated temperature minus the saturated temperature is the temperature of the liquid minus the boiling temperature. So the Weber number is given here as we define it is as function of the droplet length, and here also the Reynolds number, and this K parameter is the product of Weber number and Reynolds number. So sometimes it is also called a T, but it depends. So the details of these models can be found here in this paper. I will not go into details here because of restricted time. So we also try to do it. We did it this year, especially in this configuration. It was a configuration investigated experimentally by this lady in Switzerland in 2016, and we could carry it out using numerical simulation. And for that, we considered two injection rate and two flow rate, and this was these two situation with two temperature, T1 and 2T. These are the temperature of the flow. And here I will show you what we could obtain. It is exactly where we are. And if we say that the combustion takes place here, and we have the results, the exhaust gas come out, and we can see the evolution of this exhaust, and it's come here within this channel, and we have the injection of AdBlue, and we have the evolution of the flow, and we can also obtain the evolution of the droplets, and we can also follow the evolution of the droplets as we see directly here. I hope you are hearing me. So because, yeah, is everything okay?
Yeah, it looks fine.
Okay, nice. So now I make a short summary. So we I have shown you the evolution or the building of the spray structure of holocone liquid atomizer. And we have these two domains. We have the primary atomization here. We have the secondary atomization. And also I show you the evolution of the spray structure for swirl airflow field plus holocone. This is what we call the swirl assisted air assisted atomizer. And here it is displaying this coaxial air assisted atomizer. Here we see the influence of the Weber number of the injection pressure, and we see that we have the the dependency of the formation of the primary and secondary breakup. But to sum up, we have four major processes for liquid atomization. We have the formation of liquid sheet or jet. We have the breakup of liquid sheet or jet and formation of ligaments. We have breakup of ligament formation of the first droplets. It is the primary breakup. And then we have the breakup of this first breakup of these first droplets. We call them parent droplets in several total droplets as secondary breakup. So we see this here. Now it is a point to go to see how we can model this atomization process so that we can use this model in the codes to carry out engineering-oriented simulation models. So I refer to this book by Luc Verwisch and Dirk Rockert, in which we contributed in chapter 6 on internal combustion engine. And this is, we did it myself and my colleague and Kaushal Nishat, my postdoc here. And it was in collaboration with the group by Christian Hasse. He was at this time in Freiburg in Germany. So you can find most part of this chapter, modeling of atomization process in this chapter. We try to put some models here. I summarize them, and I will show you some examples in which we include these models and which kind of result we obtain. We have the first model. It is the primary breakup model, the blob method. So we assume that the radius of the first droplets, the parent droplets, is the same like the diameter of the nozzle. And from this, we can follow the other droplets So there is, we can say recent version include also effect of cavitation, as we say, we have spoken about yesterday, if within the droplets, some cavitation are present. So this blob model was developed by Ratz and Duan. And Duakar, it doesn't consider a detailed description of the atomization breakup within the primary breakup zone, but assume only this blob, the parent. So we can also assume some distribution function. And this is the case if we have to, for example, we inject, one very used distribution function, the Rosen-Rambler distribution. I will give you an exercise on this tomorrow. And the other model is the Kelvin-Helmholtz instability model. We call it also the wave model. So it is based on first order linear analysis of Kelvin-Helmholtz instability going on the surface of cylindrical liquid jet that is penetrated in the stationary envisaged and compressible gas with a relative velocity. There we have 3 parameters. The first parameter is this wavelength. The secondary parameter will be the formation of the first breakup, and we need also the breakup length. So for that, we have these 3 ingredients. We have the cylindrical liquid jet, we have the surface instability, and we have this droplet disintegration for the liquid core, as we see here. So for that, what we need, we have naturally the quantity we had. So the Reynolds number, particle Reynolds number, the Weber number based on the gas velocity, here based on the particle, based on the gas density, and here based on the particle density. We have the Ohnesorger number, and this is our quantity, what we defined yesterday, the if we put the Ohnesorg number and the Weber number together. And we can also, as I told you, we need what we need this quantity here, and we need also this. And from these two, we have to derive the first droplets diameter. For that, we have the maximum grow, because we had, I explained it yesterday, there is a formation of a wave, and this wave, if the wavelength is appropriate, then we have the enhancement of the instability, and then we have the breakup. If this wavelength is not appropriate, then the instability go down, and there is no breakup. So the maximum growth is given by this expression. I don't go into details of this. We have from this expression, we can derive the wave number we know we need, and the corresponding Reynolds number, radius as function of this quantity here. And then we will get the relationship between the critical radius and this wave number. And from this also, we obtain the diameter of the first droplets. So we have the length also of the breakup, this length here. It is also function of this quantity. This is a parameter, and the ratio of these two density. We have seen yesterday also that we can put in the breakup regime the wave number is function, this quantity is function of the Weber number. And if we have this, we have also the diameter we are looking for. So the other model is the holocone. It's for holocone injection. So here it is the so-called linear instability sheet atomization, the LISA model. These assume two-dimensional viscous and compressible liquid jets with thickness of two h and velocity u. They are moving through aqueous and with incompressible gas medium. Or the breakup occurs due to wave distribution, and we have also the same logic because everything is based on the instability, linear instability. We obtain the grow rate, which corresponds to the maximal instability, as these expressions, though the details are given in this paper or in this book, what I have shown you before. These K are the wave number, and which is built here. We have our sheet, and there is a building of instability, and through due to the growth of this instability, there are creation of the ligaments, and this ligament breakup in droplets. It is almost the same theory we have seen before, the sheet formation, so the ligament and the droplets, and the sheet formation is due to Kelvin-Helmholtz instability. So we have we need the diameter of sheet, as we have seen before, and we have the length of the break up. And from that, we can derive the final droplet diameter as function of this diameter here and of the Ohnesorg number. So we have aerodynamic liquid sheet stability, the ligament form and break into droplets which have this diameter. So this H is the initial liquid sheet thickness as we had introduced it here. We have the drop breakup that is for the secondary breakup. When when the droplet Weber number exceeds critical Weber number, they break up according to this expression here, the variation of the radius in the time. It is exactly this. We can approximate it as the variation of this diameter here, of this radius minus a radius which is stable divided by the breakup time. And you can see here, it is a devolution. So we have the interaction of the droplet. Here we have a first a deformation, and then we have a back grow and breakup. And here at the end, we have this kind of atomization, the catastrophic atomization. And the scenario is the same. We need the time of the breakup. If we have the back breakup, if we have stripping breakup, it will be given by this, in which the main parameter is the ratio and the relative velocity. Here it is the surface tension, and we need this radius of the stable droplets, and in this case of back breakup, and also in the case of stripping breakup, all parameters are given here. So we didn't account for the catastrophic. There is also another secondary breakup model. That is this Taylor analogy breakup model. So for that, we assume that we have our droplets here, and there we have the gas phase, which interact with these droplets, and we have compression of this, and we have we initiate a variation of the diameter of the radius, and this can be represented by this spring here. So we have we have a viscose element, and here we have an elastic element. They are in parallel, and this is what we call in rheology, like Kelvin. We have not the Maxwell, but it is it is not the Maxwell, but I will remember it. So we have this Kelvin board. Okay. We have this one. The force is acting on the spring, and it's compress it, and we have the change in the position, and this is this position, and we have R, and we have this first position is on the stop droplet, and here we have the stop droplets. What we have to do, we have to write down this expression, we know, and we make a Taylor analogy to plot, to represent this kind of behavior. It is very, very simple. So we make coordinate transformation in this way, in which we put we replace x by this expression, and then we can transform this expression in this form. And for this, we have divided by m, and if we divide by m, then we obtain all this quantity. The F, what we have here is our force, D divided by m, and K divided by m, and we have everything as we had here. And if we have this, I think we must get the expression of the equation in this form. Yes, we have this expression, and by solving this expression, we obtain all quantity we need, and we obtain this solution here. And if we obtain this solution, then we can directly also derive the radius of the current divided by the radius of the child, and we obtain that they depend of this y, what we obtain here, y dot, and we can then derive the radius what we are looking for, and it is what we put in our calculation. It is the tab model, and it is based on this equivalence with the Kelvin-Voigt body, and we can also modify it, because here what we assume it is one moment, what we assume here it is this expression, but there is also evolution of it is there is a modification of this model in which we can say that this ratio is given by an exponential law, where we say that the droplet velocity also responsible for the formation of the spray angle are derived by this equation, in which we have this quantity which is related to the it is related to the progress of one moment. So it is the growth rate. Okay. And in this case, we can obtain then the value of this breakup. And we have two coefficients, the back breakup factor and also tripping breakup factor. And we can have the critical wave number for only the back breakup, and we have also for the catastrophic breakup. So we assume this rate of product droplets creation proportional to the number of product droplets. So this here is, we obtain this as function of the child, and the change of the number of droplets is proportional to this quantity here. So the same, what is especially here, this allow to, this can be used also for primary and secondary. We have seen also that if we have the dense spray, if we are in the dense spray region, and we deal with the primary breakup and secondary breakup, then we have also collision, and we have sometimes also coalescence. This is the reason we have to take into account the collision process. And if we count for the collision process and only the binary collision, so we will have this kind of pictures where the impact factor is the B. And if we have this impact factor plotted as a function of the Wärme damper, then we have only two regions. We have the separation and we have the coalescence. But if we do this, we know that in the reality, we don't have only the variance, the coalescence and the separation, but we have other processes. And if we account only for these two, we have an overprediction of droplet coalescence, and we have it is a binary collision control volume bias approach dependent on mesh size and depth. And in this case, we cannot take into account, for example, the other process we can account for. And these processes are, for example, reflective separation, stretching separation, and the impact factor here is modified. This collision regime map as modified by Munamura is given as we have here. We have the bouncing we have a coalescence, we have a reflexive separation, and we have stretching separation. And for that, we have developed not this control volume-based approach, but we have developed this kernel-based modified collision scheme. This scheme allows us to account for all these processes and not only on these two processes, which can be very captured by this control volume-based approach. So the details are naturally in this paper here, and we did it, and we compare with experimental data. By comparing with experimental data, so we obtain first the velocity of the velocity of the droplets in below the injector tip, and after that we could produce the morphology of the spray from the simulation, and we could compare with the experiment. It was a work we did with our colleague in Karlsruhe and now in Aachen by Nea, and we did it with Nishad and myself. And the measurement were carried out by Pischke, and for the spray structure, the droplet distribution, and the droplets also velocity, the spray penetration depth, and near nozzle velocity as well. We use for that the combination of the LISA model for the primary breakup and the tab model, and we include this droplet-droplet interaction, and also we include evaporation model. And for that, we obtain exactly what the experiment have shown at two different positions in the two different pressure. We obtain the correct probability function of the droplet distribution in this case, and at 10 bar, and we obtain also the correct spray penetration depth corresponding to experiment, as we have shown here and published in us. To conclude, I think I have still 2 minutes. So to conclude, we can say that using these different models, we could obtain the correct penetration length of the jet, and we could also obtain we see the variation of prediction obtained by if we use different models. So the question will be, which is the correct one? So that is very difficult. And due to the fact that these models include different parameters, and sometimes these parameters are tuned for specific configuration, and that they cannot be used for all configurations. And first remark here, the tab model really the right Dirac model and the wave model, they do not distinguish between the two processes, I mean the primary and secondary breakup. The model parameter depend not only on nozzle geometry, but they also account for numerical effect. And naturally, as I told you, they include different model parameters. The other models like these enhanced tab, which I explain a little bit, in which we include an exponential variation of the number of droplets, and this model here, fractionament induced by acceleration, and the Kelvin-Helmholtz and Rayleigh treat primary and secondary breakup regions. So the LISA model can also be used for both, but normally we put also a secondary breakup model. So this, at the end, that is what we can say in to put them together. And I would like only to go to this Riddiwaka, that is this droplets model. And we have also Kelvin Helmholtz model. And we have also this Kelvin Helmholtz model. And at the end, I would like to show some effects we see here, that we change the pressure and we could get the penetration depth. But we can also try to deduce some correlations. So the correlation for the penetration lengths, there exists for the jets or for the jet in cross flow. And there is also some correlation which account for the effect of the pressure. And this is one which was proposed by Hiroyasu in 2000. And we see that we have two parts here. The first one is evolution of the penetration lengths linearly to this quantity. And we have a second part, which is proportional to this quantity here. And you put both together. This is valid for this part before breakup, and after breakup, we have this profile. And the coefficients are given by this ratio. This ratio L to D, the breakup time is given by this expression here. And we see that change the different pressure in injection pressure, 35, 30, 20, and you obtain very good results where you compare experimental result and numerical results. So I can close here, but to close, we see also here the relation of the penetration lengths with their volume fraction. And this is a recommendation from the ECN group, where we can calculate the penetration length based on the volume fraction we can obtain. If we have here, for example, the X direction and it is Y, we can calculate this integration at different X position, and we can give us some limit. We say the strength holds is, for example, alpha, the level, the volume of fluid must not be larger than 0.3 or 0.4. And if I give it, I put this here and I calculate the position where I will find this quantity, this limit. After, if I don't, all quantity less than this, I can say that there is no spray, and I say, okay, I can then define my penetration length. So we see that the threshold is arbitrary, but we can choose it to attempt to match some experimental data. So that is what I would like to speak to you today. And I am now open for some questions. I see here there is, I will decide which wave is short wave and which is long wave. If there is any criteria by which we can say above certain wavelength wave is called long wave and below which is short wave. Okay, wave number A is corresponding to maximum wavelengths. Wavelength, I will proceed. Okay, first the question is the difference between short wavelength and large. So we are here. Here. So the question is, what is the criteria to distinguish both? So the criteria is one moment. So the criteria is given by this expression here. Okay. We see that we have the short wavelength, and here we have long wave. So it is defined by this criteria. So the other question was, what is K? I think K should be, it is related to the maximum or, let me go. So we are here, or I don't know where we are, because I introduce also another criteria here. About, oh, no, here. I'm looking for the breakup. Here. So on which page you have your question? I don't understand. I thought perhaps it is in the in this
You can talk. I have allowed you.
yes.
Actually, sir, I want to know that the maximum wave number is like formula is k is equal to 2 pi by lambda. So here we are using smallest wavelength or maximum wavelength, like
Again,
like wave number formula k is equal to 2 pi by lambda, as I know. Like lambda is here the maximum wavelength or smallest wavelength.
so acoustically, I could not understand the question.
Yeah, so may I rephrase that?
Yeah, yeah.
Am I able? Yeah, so what his question is that typically for the wave number calculation, so if the wave number is, let's say, k, that's
Yes.
equal to 2 pi by lambda. So this lambda, his question is that it should be considered as the shortest wavelength or the largest one. That's his question.
So I would like to know where we are first. This question, so we have k wave number for maximum.
Yes.
So,
Maximum correspond for what? Like maximum wavelength or?
yes, this corresponds for the maximum growth. So is clear?
Okay, sir. I have one more confusion, sir, related to that one. Where we are calculating first one, like short wavelength or long wavelength. If let's say we have calculated the wavelength, and I get like some numeric value. So how we will able to decide that this numeric value will come under the short wavelength range or long wavelength range?
So you can also interpret. Josh, okay?
Yeah. Yeah, go back to that particular slide.
Which one?
Yeah, the one which
First one, I think, sir. First one.
go back.
Today's first lecture.
Yes, here.
Here?
Yeah.
No, sir. First lecture today's first lecture, where we are deciding the short wavelength as long.
At the beginning.
Yes.
So here.
Yes, sir.
Yeah.
So here there is some empirical formula, but if we calculated the wavelength from any formula, so how we will able to decide that the this wavelength will be come under long wavelength length or short wavelength length?
How we can decide.
Yes, sir.
So that is what I say. So from the long wave theory, we have this ratio here. Okay. If it corresponds.
Okay, sir. Okay. Sorry.
Yeah,
Thank you.
You okay?
Yes.
Okay. And for the short wavelength, we have this dependency. Okay. Other questions?
Yeah. Is there any other questions? Or so maybe you can raise your hand or you can type it. Yeah. There is no more question. Then we can move forward. Actually.
Okay. So I thank you then.
Yes.
Tomorrow with me, but today I think in 2 hours.
Yes.
The introduction in turbulent combustion.
Yes. So
in turbulent modeling.
yes. So okay. So still there is a question. I want relationship of breakup length with injector pressure.
There is another question here. See.
Can you see that?
Relationship of breakup lengths with injector
pressure.
Yeah, that is what I produce at the end, I think. Today.
That was the penetration length, I think.
Yeah. Is the relationship between penetration length and pressure, injection pressure. Okay, and
sir,
yeah.
Penetration and breakup length is different.
This is the penetration length. And the dependency with the pressure is here. And first we have two regions. The first one is what the breakup time, and after the breakup time we have this. And this is, we have the parameter alpha, depend on this ratio here, and this is the time of the breakup. It is depends on this ratio of density, and here also the pressure. And the different coefficients are given here. I think this transparency is not available for you, but I think what I can do is perhaps to, so first, is the question, do you get your correct answer?
Yes, sir.
Okay, yes. And do you have, so you will have it in the presentation. I think it is recorded.
Yeah, it is recorded.
Yeah, okay. Other questions?
So
last one, the dependency of the penetration length and L to D, that is first here, but also as a function of the volume of the liquid volume fraction. So we have two expressions. We can get it as a function of L to D, but we have seen yesterday that L to D ratio is also related to their liquid volume fraction or particle volume fraction. If we have this L to D, then we can have it as a function of alpha. Alpha is the liquid volume fraction. And in this case, we can do in this way. That is our alpha, and we can obtain them timely as function of the penetration length as function of the evolution of this along the axial position or the axial direction. So, other questions?
I think, oh, there is one more. Ravi.
May I get the answer to the last question I made yesterday? It is related to a function asking if it can go to infinity in case there is no evaporation and the droplets are traveling with no more backup. If they are no, it's a practical case. You cannot generate a spray with the infinity penetration length, because so you are generated it will impinge a wall, or it will impinge the board, something. So, and this will be stopped there. So if we can open his microphone and perhaps tell me again what you would like to say.
So can I speak, sir?
Yes.
So the question is like, in case it's a co-flow situation and the droplets are being carried by the air itself, the medium, or the continuous phase, and then the droplets are traveling through and are being carried. So, I mean, there's no relative velocity, you can say, and in that case, will that be considered the maximum penetration length will be infinite? I mean, traveling through the air itself, and where the air is going simultaneously, the droplets are also going. So means they will reach somewhere where this air will stop. So it's like, I mean, I don't understand. Maybe the relative velocity is zero, where the relative velocity goes to zero, that will be considered the penetration length. Or, I mean, I'm really, I don't know if I'm able to deliver the question properly. Say the situation is to simulate, and there can be a some limited, or you can say I can have some wind tunnel experiment, and it's wind is entering from the inlet and going to exit, and the drops are passing through the outlet itself. So that means that domain itself is a penetration length.
Yeah, in this case, yes.
Okay, but droplets are also going out, so there's the domain for simulation, let's say.
Yeah, this is the domain for simulation, and this gives you the length of what you would like to get in this case.
Okay, but penetration length in that case, I mean, because I'm not able to simulate after that, that means the penetration length is limited by the domain itself.
Yeah, you stop there, but if you continue, so you will get a maximum distance. Okay, that is perhaps what you mean.
Okay, yeah, but that was the issue that
So,
say the.
let me show you. If you have, for example, it is going in this direction, okay?
Okay.
And at infinity time, so it will go so, okay, to this maximum. The maximum value where you say, for example, there is no more entrainment of the particle or of the droplets by the air. But what we are showing here, it is within the control volume, there's a computational domain.
Okay, so means the penetration length itself is limited by the computational domain itself.
Not only, but they are engineering configurations, so they are limited either by the
Okay. Okay, so okay.
or by some other processes. But what you, I think it is in the environmental domain, perhaps in the aerodynamics. But in aerodynamics, so I think it should be also by your control volume. So because you have a chamber, okay, you have your tunnel, and it is limited by this. For infinity, I cannot accept that it may be. It is not possible.
Yes, sir. So
Okay.
thank you, sir.
Yeah.
Yes, sir.
So, do you agree with me?
Yes, sir. Yes, sir. Not an issue. Thank you, sir.
Okay, thank you. So, other question, I don't see any other question. Then
Yeah.
I,
There is no more question, I think. Yes. So I will, that I will give them some turbulence modeling and then some turbulent combustion modeling, right? That's the idea. Hello?
yeah,
So I will talk then turbulence modeling and turbulent combustion modeling.
yeah.
Good. Okay. Okay.
So you will start with.
So
Rasmus?
tomorrow, yeah, tomorrow you then try to join around 11:30 in your time.
Okay, 11:30. Okay.
Yes, by that time. So today you don't have to come back, then afternoon session. So I'll okay.
Okay. You will always tell me the content of what you are speaking about.
Yes, so I will share that.
So that I can sometime refer to what.
Sure. I'll once I finish, I mean, after 2 days, this one I'll share. Then you know what
Okay.
I'm going to plan to.
Okay. Thank you.
Okay. Thank you.
Okay.
Yeah.
Bye.
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 Okay. So let's continue. These things on turbulence part. So what I will do now. Okay. So what we'll go about is that, so first, I mean, basically talk about what is turbulence, and then, yeah, stop sharing from here. Yeah. So how do turbulent flows behave? And then probably we can talk about essentially the fundamental, some of these features that turbulent flows which are associated, and then how we model them. So why these are important? I mean, there are a lot. I mean, obviously turbulent flow cannot be talked or discussed about over few hours. So the idea here is that give you some idea about how this turbulent flow, these are modeled and behave, so that you can kind of correlate with the turbulent combustion modeling, because these are the building blocks for your turbulent flow modeling. So if you look at the turbulence, this is a very classical picture of flow around these things. So where you see this friction diagram with the effect of Reynolds number here. If you see, this is the Reynolds number where you have this friction factor. So how the flow actually changes their behavior. So especially this particular figure, if you see the wick. So here's a sphere and the Reynolds number is quite high. So behind the sphere, how the flow behaves actually. So now what it does, the turbulence essentially, again here if you see, this is the wake pattern. This is, you see at the very high turbulence Reynolds number, that is at the some are 30,000, and this was a half of that. So once you make it more and more turbulent, obviously for this simple kind of geometry, the sphere, the drag actually reduces. So the force which is getting acted on it, so that gets reduced. So that's how the turbulent flows are kind of quite attractive, and sometimes we use that. These are another classical example of the turbulent flow behavior which you see in the nature. So one hand you see this volcano here, and the other one, if you see, this was again the plume which is coming out, and these images can show you how the flow actually behave like a turbulent flow. This is some of the another example where you see the smoking of cigarette, and then when the aircraft actually flies, actually how much the downwards gets kind of this kind of vorticity underneath of the airplane. So this creates this vertical structure. If you see this nice structure which has been created here, obviously here also. So these are going to give you an idea about the flow characteristics of this turbulent. Now, one of the important things for the turbulent flow is that the scale similarity. So if you see, when I have a Reynolds number 4300, and when I go to Reynolds number of 10 to the power 7, which is essentially the 10 million, there is a similarity of the structure. So this is called the scale similarity. So you may have the flow to be turbulent, as you go or increasing the Reynolds number, but the structure, it looks like there is a nice similarity. Obviously the scales, they are not same. We'll come to that very quickly, but there is a scale sim. Now, this is another classical picture which probably you now these days get into the textbook, where the flow from the transition to, a transition from laminar to turbulent flow. So these are the different kind of waves that pattern you see. So now, so here one important thing is that how we characterize the scales and all these things. Obviously one can, in a simple language, one can think about when you increase the Reynolds number, then you get more and more the flow to be turbulent. So that's how one can talk about. So, and if you look at this particular case, this is an example of this is called the free jet. So that means the jet is coming out and in the open atmosphere, and the flow is turbulent. So what happens is that to characterize the flow field, you sometimes actually take the time series of the data. And if you look at the time series of the data here, so this is quite, interesting to observe. The data looks quite, noisy. So there is a lot of noise there in the data. So this is one of the characteristics of a turbulent flow whenever you look at this signal. And more importantly, they are going to be unsteady in nature. So it's not like that they are. So if you kind of, from this example, if you try to say that what are the properties of turbulence, obviously one of the important properties that is going to be unsteady and three-dimensional. And when you say unsteady and three-dimensional, all these are kind of a subset of that they are going to be irregular and chaotic. There are large scale structure, there are small scale structure. So everything in total that you can say that obviously these large scale structures are the macro structure or the large ADs, whatever you call. So they are mostly dependent on the geometry of the of your interest. And if you have a small structure, they are more like an universal in nature. So why we say the large structures are geometrical dependent? Because if you say, let's say, just you have seen the example of the flow around the sphere, at the same time you have seen the volcanic eruption. So there are the two different kind of geometry where if you think in terms of the fluid mechanics point of view, there are two different kind of geometries, so the nature and characteristics are different. So that is why the large scale structures are different. And obviously the flow or the turbulence is always going to kind of more predominant at the large Reynolds number or the high Reynolds number. There is a dissipative in nature, okay? And sometimes actually we prefer turbulence to be there. For example, if you talk about the gas turbine engine, if you talk about the internal combustion engines, you talk about sometimes the flow around the aircraft, flow around any other geometries where sometimes you prefer the turbulence to be there. Because the presence of turbulence actually helps. Okay. So now if you have a coordinate systems where you kind of, these are something, the conventional and the, Cartesian coordinate systems. So you have this material derivative of any variable. So so if you look at your typical fluid flow governing equations, so in an incompressible, obviously I'm talking about incompressible governing equations. So you see this, then these are your continuity equation, or you can talk about the mass conservation equations, and these are your momentum equation. And you have the other these things, the pressure, which is. So what is important here is that you see how many equations you have. If you talk about the three-dimensional flow, you have 4 equations and there are 4 unknowns. So which means you have 3 components of the velocity and the pressure. So the system is closed system of equations for a given initial and boundary conditions, you can find out. So what happened is that whether you call it a well-closed problem or not. Okay. So when we call these are all partial differential equations. So if you say these are the well-posed problem, then your solution has to be there. That means the solution, existence of the solution is there. Solution is unique. That means there is only one solution which is there. And also, if I have some sort of a perturbation in the system, the solution is going to be, due to some small perturbation, the solution is going to be stable. So what it says is that your Navier-Stokes equation is a well-posed problem for laminar flows. But at the same time, if you go to turbulent flows, this is not well-posed. So this is ill-posed. Why? Because the turbulent flows straight away do not satisfy this condition which is mentioned at C, this condition. So your turbulent flow actually doesn't satisfy that. So that means if I do some small perturbations or create some small perturbation there, then the flow is going to be more perturbed. So in a nutshell, one can think about, one can say that turbulence is nothing but a deterministic chaos. And why this behavior is more with the behavior, one can correlate with this nonlinear term which is sitting in the Navier-Stokes equation. Now, if you kind of convert non-dimensionalize the Navier-Stokes equations, which are kind of very much available in any textbook, so I will not go into the details. So what is important, in a non-dimensional form, I can write the equations in this way. So what it says that when you talk about the Reynolds number similarity, if for 2 flows, Reynolds number and the scale, the scale initial or the boundary conditions are same, then your scaled velocity and pressure fields are the same as well. But when you go to large Reynolds number, So you have the viscous term, which can be negligible at the large scale. So there is a scale similarity because there is no dependency of the Reynolds number. And also there is a macro scale structure similarity. Now, another important aspect when you see those example of those, the turbulent flows is the vorticity. So this is how you define the vorticity, which is essentially, kind of the cross product of your velocity field. So it's a curl of the velocity field you can think about. So vorticity also can have a transport equation, and that transport equation having different terms. So this term which is highlighted here is called the vortex stretching term. And this term is going to be present if your flow is three-dimensional. So what this vortex stretching term does, because this is one of the primary driving force behind your flow, or change in the vorticity of the fluid particle. So through their stretching and rotation of the parcel. So other hand, or on the contrary, one can always say that vorticity could be a sort of representation for my turbulent flows. Okay. Now, if I simplify the situation, if it is a potential flow, then my vorticity is not there. Then I define a velocity potential. Now, if you use some algebraic relations and all these things, so for potential flow Navier-Stokes equation, you get this kind of equation. Okay. Now, similarly, if I extend these things for the variable density, okay, so still I can be at the incompressible range, but the flow could be variable density, which is a primary example of your laminar laminar burning system. For example, the candle burning. This is a very, simple example where your flow is laminar, but it's a variable density. So obviously there would be change of the density that you have to take into account. For that, you have to take into consider the energy equation. And we bring into the Boussinesq hypothesis, which will correlate your density variation along with the temperature variation. Because end of the day, the variations are due to the temperature gradient. So that variations are taken into consider through all these approximations. So what it does, that the equation systems are going to be a little bit changed. So you have the continuity equation, then the momentum equation you get in this extra term. This extra term is nothing but your buoyancy effect, which is essentially kind of getting induced due to your temperature gradient, and then you solve for the temperature equations or temperature difference equations, whatever is this. So you have variable density flow, then you kind of, now as we have said, all this we have already talked about. The turbulent, there would be flow, be three-dimensional, chaotic, large-scale structure, small-scale structure. Now, at the high Reynolds number, you have the scale similarity. That is what is shown in these pictures. It would be dissipative, and obviously turbulent helps in mixing and things like that. Now, there, one can do some simple analysis to try to analyze this flow field. So one of the things to try to, one can answer is the flow stable for a small perturbations. We said that when we are talking about the definition, we said that the turbulent flow fields actually do not satisfy that criteria. That means if you perturb the flow field little bit, then it's going to be more perturbed. So that is, one can look at it through some stability analysis. So there are simple stability analysis. So these are the type of stability analysis one can do. So you can have linear stability analysis, normal mode analysis, then there could be inviscid and discrete. So I'll just quickly go through that when you do or take care of this kind of stability analysis, so what are the equations you get? So what is the base, the idea behind that kind of stability analysis, that you have a kind of, you get the flow, whether you call it the base flow or basic flow. So you get the function of the flow space and all these things. Now, suppose on this particular small, so you add some small disturbance. That means I have a flow field here, then I will add a small disturbance to the equation. So then I will linearize the system. So what it does, that when you linearize the system, this is going to give you a linearized equation, or essentially it turns out to be an eigenvalue problem that you solve. And then we try to find out the non-trivial solution. And what you try to see, if that flow is unstable, if solution grows in time,
If not, then the flow is stable. So that is how the linear state. So when you look at these examples like the jet, this is you see in the atmosphere, this is smoking from cigarettes, and this is what you get. These are the photographs of KH instability. I think you have been already listening to this KH instability for yesterday. This is called the Kelvin-Helmholtz instability. Wherever you have this gradient of the velocity, then you tend to get this kind of Kelvin-Helmholtz instability. And turbulent flow field is a clear indication of that, where you get to see this kind of instability. Now, how we kind of, as I said, you have a base flow field, then you kind of add some small perturbation. So if you start with the inviscid flow, and that's how the modal analysis is done, and these are the linearized linearized Navier-Stokes equations, or you can say Euler equation that you get. So you don't have the viscous term here. And then if you kind of extend this further, then you get this is the Rayleigh stability equation, which is solved as an eigenvalue problem. And if you include the viscosity there, then you get this equation, which is very much known in the Orr-Sommerfeld equation. So if somebody is done the boundary layer theory, or if you go to boundary layer profile, so finally you try to solve this eigenvalue problem, which is going to be a function of the wave number and Reynolds number. And we try to see what is the critical Reynolds number, and then this eigenvalue problem. So this is an example of a Poincaré flow, because just to note here, these are something, one can actually carry out those stability calculations and find out this kind of graph. But here we want to just show that what happens when you carry out those things. So this is a simple flow in a Poiseuille flow. And you see, this is the curve where you get the stability margin. Okay. So one side there is a flow is stable, other side the flow is not stable. Similarly, if you take it to the stability diagram, the Blasius boundary layer over a flat plate, you can see this is the unstable zone and the outside is the stable zone. So these are very classical example, and these have been kind of studied over the years, and you have very established data for this kind of problem. And now this is another, the picture where you see the tall interesting waves and the turbulent spots in the Blasius boundary layer. You can see the flow comes here, and this kind of waves would form. So what it goes through that, it goes through these waves, and finally it turns into the transition to turbulence, and that's what happens. So now, if you talk about the scaling, obviously these are the pioneering people. Starting from Burgers, then Richardson and Kolmogorov, they kind of given different scaling theory. So this is what we actually, even today when you talk about turbulence and things like that, that is what. So, and obviously top of that, we have that energy cascade theory, and Kolmogorov came up with their theory in 1941. So one of the things that we talk about the scale similarity, if you see, there is a 2 times of the Reynolds number between these two Reynolds number. If you visualize the macro and microstructure of this mixing layer, so there is a scale of this turbulent motion. So when you increase the Reynolds number, the range of scale increases, but there is a similarity of the scales of the structure. So this is called the scale similarity. Okay. Now, what we talk about the energy cascading process, it's very simple. That turbulent flows always having the extra bit of energy, or it carries the energy. So energy comes from where? So it comes from the large eddies. So these are the, this is a schematic of a representation of that kind of. So you have this length scale, time scale, and all these things. And the large eddies where it is formed because of, that's what we said, the macro structure are dependent on the geometry. Because if you say you have a large diameter of pipe, the flow comes out of that pipe is going to create the large scale structure of the order of the diameter of that pipe. And if you see the large structure which comes out of a smaller pipe or smaller diameter pipe, the maximum size of the eddy. So this is what the characteristics length which represent that. So what I'm talking about, let's say a pipe of having a diameter like this and pipe of having a diameter of like this. So there is a difference. So these are going to, these geometric definitions are going to give you the large scale structure or macro structure. You call it a large scale or macro structure. So the largest size of the eddy that is going to come out of this kind of flows is going to be order of that characteristics length or the diameter. Now this macro structure actually carries the energy, and then it breaks down to, or rather due to through this vorticity motions, this breaks down to the smaller structure. And then finally, smaller structure breaks down to the smaller AD and smaller to further smaller structure. And finally, that gets dissipated. So this is what called the energy cascading process. So that means what I try to say, so first you have this large structure which are having the largest energy. Now energy cascade down. So the large structure to small structure, small to small, and finally through the viscous dissipation or heat dissipation, that is actually goes away. So this is how the energy cascading process or the energy transfer process which takes place in the turbulent flow. So that means that's what when you say the macro structure are very much dependent on the your geometry. So the macro structure carries the large amount of energy, and then it actually cascades down to the smaller kind of structure, and through dissipation it's gets. So this is again a nice classical picture of Leonardo da Vinci. So where I mean that many years ago, he kind of visualized this kind of chaotic nature of the flow field. So here he talked about observe the motion of the surface of water, which resembles that of air, which has two motions, of which one is caused by the weight of the air, the other by the direction of the curls. Thus, the water has eddying motions, one part of which is due to the principal current, the other is a random and reverse motion. So ideally, what it talks about that the people try to visualize this kind of flow and see, and this is the rhyme of the Richardson that talking about or characterized the turbulent flow. Now, when you talk about what is the primary mechanism behind the energy cascade, as I said, it is the vortex stretching. So if you take an eddy as a closed vortex tube like here, and you level that to level 1, and then when it is getting stretched, it takes a shape like this. So you can think about a tube which is a flexible tubes made of rubbers or things like that. So when it's stretched, or you can think about the balloon, when you pressurize, it actually elongates. So same thing happens here. So the vortex, since they are also having a transport properties and they are getting transported through the governing equation, so this is what the stretching mechanism takes place. But the total velocity remains constant, because that is something of the flow field of these things, and you also can have the total kinetic energy. So what it happens when you're having this motion, obviously we know all from the first law of thermodynamics that the energy has to be conserved. So if the large eddies are dissipating or out the energy, then the energy has to be consumed by somebody else. So that is what is happening. So large eddy, they are going to lose out the energy, and at the same time the small eddies are going to absorb that energy, so that in totality your energy conservation takes place. Okay, so also here you think about the vortex state. So this is a flow inviscid, between an unstable, inviscidly unstable, because the cage instability. So the vortex seats actually rolls up like this. So what happens is that when it rolls up, it generates new vorticity, and the process repeats itself. And when new vorticity is generated, they are also getting transported, and there is a vortex stretching, which actually stretches is out to generate smaller eddies. So this process continues in turbulent flow. Now, how do we scale it? So that's a very important aspect of the how do we scale it, because the scaling of macro structure and the energy transfer rate, they are important. So typically, as I have said already, the macro structure is order of the characteristics length. So if I have a flow through pipe of, this is a pipe which is this diameter, then this length would be order of that diameter. So, and if you have a flow over a cylinder like this, okay, and this is the diameter, then this L naught would be order of that diameter. Let's say the DC, this is the cylinder diameter. So that is why we say the macro structure are very much geometry dependent. So what happens is the energy of the large eddies would be of that scale. So the lifetime of the eddies, you can find out that this is the energy transfer rate, and this is what you kind of estimate through the energy dissipation or the energy transfer rate of the eddies. So yes, the energy are also in a variable density region. They can be that can be transported across the variable density region. Yes, that is true. That is the question from Ashutosh. But there is another important thing, because when you talk about that variable density flow, there will be an extra term which is going to come up, which is called the baroclinic production term, which is a cross product of density and pressure gradient. So that, since I was just considered the incompressible flow, that term I have not shown. So the vorticity transport equation is still valid, but there will be one more extra term in the right hand side. Okay, so that was going to be kind of, you kind of make it active in a variable density flow or the reacting system. So in a reacting system, that term is going to play an important role. Okay. So now, when you scale the smaller eddies, this is where Kolmogorov hypothesis came into the picture. So we said that the smallest scale of the turbulence are the Kolmogorov scale, and then we have this defined as the eta, and then that the small scale, what would be the velocity? So we call it a u eta. Then the time scale is the tau eta, and the Reynolds number at there is. And you can find out a nice correlation between your macro structure and the smallest structure. So in terms of your Reynolds number. So why this scaling is important? Because whenever we try to simulate, especially in the modeling, whenever we try to model these things, the understanding of these large scale structures, and so that would actually determine of your grid size, that what is the grid that is required to resolve how much of the energy. So that I will come when I talk about towards the end of the turbulent modeling and things like that. So these correlations of the between the macro and microstructure. Now this will give you a very nice representation of that. Already we talked about the energy cascading process. So, and if I, let me see, okay, so if I draw another curve here, which is the energy with the wave number or length scale, so the curve looks like this. So these are the boundary, and this boundary is essentially energy containing range. This is the boundary of dissipation range. So this is what you are kind of shown here. So your large scale structure which are sitting here in this particular zone, they are the one which are going to carry the majority of the energy. And this is your energy containing range. This is your called the inertial sub range, which is this, and then finally the dissipation range, and it goes to the the smallest size of the eddies, which is the Kolmogorov size, and then they get dissipated. Okay, so you can always nicely correlate the time scale. So what it happens, this picture shows you a lot, because there is a production of the energy which comes to the energy containing range. Then there is a energy cascading process or the energy transfer process which takes place here, and then finally through dissipation is actually dispersed. So overall in the system, the energy conservation is done. Now, if you, already we have talked about the scaling. So we talk about with the macro scale structure, with the small scale structure, we can scale their time scale, length scale, and all these things. Now, what Kolmogorov proposed in 1941 is that there are three hypotheses. So one is the local isotropy of the macro structure. That is very, very important. Okay. And then there would be the first similarity hypothesis, where the statistics of the microstructure have a universal form. That means the microstructure are going to be more universal in nature. And the third similarity hypothesis, that is scales in the inertial subplanes are uniquely determined by dissipation, epsilon, and the size of the eddy L. So these are the famous hypotheses which are proposed by that. Now, if you try to, we have already talked about that the turbulent flow are going to be chaotic, they are going to be random in nature. So obviously the time series signal that we have seen also quite kind of chaotic in behavior. So we can have these signals and do statistical analysis. So these are the statistical time series signal of a, signal of a turbulent signal. So what you do, so you can kind of capture this kind of signal, then you can do some sort of a running average or time average of the data. That means you take the sample for a longer, signal for a longer time and try to see the time average sense, and you can get a mean velocity on time average sense. Similarly, so if you talk about this time average series, then the question comes how large. If the time averaging is too small, then the slow fluctuations which are maintained in the averaging. And what is desired is that average out all the turbulent fluctuations if your T is infinite. So there is always an checks and balances that one has to be careful how long you do the time averaging. So if you do more time averaging, that means it's just like you think about in a very simple example, in a class, you have 100 students. Obviously, the average is going to be lower. If you have 10 students, the average is going to be always higher. Similarly, if you have a too long of time series, then you actually eliminate out the unsteady nature or the fluctuating natures of the field, and you get a smooth flow field. So this is what happens if you do a lot of time series, then you get a smooth field like that. Okay. So there are different averaging techniques. So one can do line averaging. Okay. So one can do ensemble averaging, which is quite popular in turbulent flow modeling, that it's like you take a different snaps or series of data and then you kind of ensemble that. And this is quite often you do somebody is doing in experiments, you capture different snaps or pictures and then you kind of try to ensemble that and get that ensemble averaging data. Now, when you look at this time series data and turbulent data, they are quite stochastic in nature. So we always talk about the probability density function of that. So this is how you define the probability distribution of that particular velocity field, because this is going to be required when you talk about the statistical model for turbulent combustion. Okay. So the definition, which is based on mean PDF, then you can always get back the macro property of the mean flow field. So if you have a probability distribution of that, so it is just going to take you for a different interval. Let's say if you talk about this different interval, what is the probability of having a particular situation? So once you get this probability distribution function, you can find out these various variance, you can find out the RMS. Then at the same time, you can have the covariance between two velocity components in space or time. So then this is called the covariance, so this is the joint PDF of this particular, and you can find out the correlation coefficient as well. So this going to connect two velocity component at different spatial location. So at different spatial location, how they are correlated. So this is going to be, whenever one has to, or someone is interested to characterize a turbulent flow field, it is a good idea that you kind of try to get this kind of correlation, which gives you an idea how nicely you can correlate these things. So obviously, these are some of the special situations where statistically it is stationary turbulent. So how the probability density function is going to, that's going to be independent of time, or if you have statistically homogeneous turbulent. So which is going to be independent. So this is independent of time and this is going to be independent of space. And that's what we call it. If a homogeneous turbulence means any direction you go, there is a uniqueness in the nature of the turbulence. And when we call it statistically stationary, that means with time, that is not more varying. The turbulence level has kind of set in. So now you can have stationary process and you have the homogeneous, homogeneous process. For both the cases, whether you do the time averaging or you do the ensemble averaging, they are going to get you back the same thing. So that's one of the things, and that is what's when you talk about, so whenever you kind of try to identify the turbulent flow field, it's very, very important that you use this term very carefully, whether it's homogeneous or non-homogeneous, whether it's statistically stationary or unsteady, that can say a lot thing. So one of the very common way of kind of looking into these things are doing the Reynolds decomposition. So what you do, you have an instantaneous flow field. So you kind of decompose in, one is mean component and another is the fluctuating component. And these are the properties that one has to satisfy. So the, and then, but the time average doesn't satisfy the fourth condition, which is this condition, because of the double the integration inside that. But if your T is, or the time of averaging is much larger than your integral time scale of turbulence, which is the time scale of your large eddies. That means what is the time scale of the large eddies to dissipate out the system? then the error is small. And ensemble averaging doesn't satisfy the all Reynolds condition. So that's basically another important parameter. Now, which we often see, these are my incompressible Navier-Stokes equation. Now, if I use those, and this is for mean flow, now you can actually use those decomposition. That means I can use those u plus u prime, and for all the variables, then I get back these equations for the mean flow with the average quantities. But there are two terms. One is the temperature equation or energy equation. Another term in the momentum equation. These are going to be the Reynolds term because they are not closed, because they remains unclosed. So if you rewrite this term, so they are momentum equation. If you see right hand side, these are kind of known, which are going to be the molecular stresses, and this term is particularly termed as the Reynolds stress or the turbulence stress. So what it says that whenever you have the flow is chaotic in nature, so you have these fluctuations are there along with the mean flow, that essentially one can think about it's going to induce an extra additional stress on the fluid particle. So where does that originate from? It originates from the transport of the mean momentum by the turbulent fluctuation. Okay, so now how it happens, if you clearly see, so if you have an example of the flow field, which is a, mean velocity profile like that, and let's say you take a particular location here, and these Reynolds terms are always kind of taken in the negative sign with that nature. And why that happens, let's say a particular fluid particle here, which tries to move in this direction. So obviously when it moves in this direction, your V prime is going to be positive. But at this particular, since this is the velocity profile, so at that particular location, I have some del u by del y, which is positive. So that means there is some u which is prevailing there. So now if you want to conserve the momentum, then obviously u prime is going to be negative. Same happens when I go in a reverse direction. The fluid particle pushes to or downstream, that means it moves with a negative B prime, then the other way around, u prime is going to be positive. So that's what the negative sign appears in the Reynolds stress term, because that is the physical interpretation what happens when you do this. So finally there, if you look at the closure problem of this Reynolds average equation, so these are the terms which remain essentially unclosed. So you require some sort of an extra equation to close this term. So how we do that, and that kind of gives rise to your closure terms of the different kind of Rans model. Okay, so you have this definition of the molecular stress, you have the isotropic component, and then this is called the shear stress component or the deviatropic component. And now if you look at this turbulence stress term or the Reynolds stress term, so you divide that in one is the isotropic part, which is the turbulent pressure, one can think about that way, and this is the deviatropic part, which is the turbulent shear stress. So using the Boussinesq's hypothesis, you finally close the whole term like this. So you get the extra term in terms of eddy viscosity. So then if you couple that together, so this is same thing we have the couple that together with the main flow equation, then your right hand side, this in a turbulent flow equation, if you look at, then you will have the effective viscosity, which is in terms of the molecular viscosity and this turbulent viscosity. So this is what the scale of the large scale. Now in free shear flow, so these are essentially the free jet. You can see what happens at the wake. This is the, this is jet and this is mixing layer. Mixing layer means two different fluids they are mixing. So you see the nature of the flow, and the importantly in this particular, you see the profile, velocity profile, how it looks like. Okay, so this is the typical round jet profile. If you have, these are there in the classical book. So this looks like that. So this is how you, the jet comes out like this. If you see that example, and as you go along the downstream direction in this, so the profile. So initially you have a much higher velocity, and slowly because of this energy transfer process, so the velocity also, where does that, where does this flow getting energy? Because it is getting energy from the mean flow field. So when the turbulent energy picks up, then the mean flow also getting reduced because it has to lose out the energy. Ideally, the energy has to be conserved. Now this is a planar jet profile, and you can see how the profile looks like. So I just give you an example here. So how would you kind of handle this kind of situation? Analytically, one can do, so you can do some simplification, though, like you can have a mean flow field in 2-dimensional, you can see the statistically stationary, you can see the statistically homogeneous in z direction. So then you simplify different terms here. As you see that all these terms are simplified, and then finally, whatever terms are left over, you use order of magnitude analysis. So you can do order of magnitude analysis to find out the solution. So if you do so, this is a typical solution, that similarity solution that you get for the plane turbulent jet. And now here you see the scale similarity, which we have been talking about. So you see the Reynolds number, which is increased by 13 times. Here it is 10,000 times, but there is a similarity in the scale. This is what is called the scale similarity. But the size, I mean the scales of different flow would be definitely different. Same way, you see the turbulent wake past a sphere, which we have seen that example. This example also we have seen how the example of the wake behind that seat. Okay. So now wake, if you have an obstacle like this is an uniform flow, and you have an obstacle like this, then you can see the wake, what is going to be look like. So there is always a profile which is going to give you a velocity deficit. So this is what you capture in the wake profile, and this is the self-preservation. So this you can find out from the literature. These are not important. Yeah, another thing what you can get to see in the wake is the intermittency of the near the edge of the wake. And so these pictures are taken from a classical book of Tanekes and Lamley. So this is a very nice book. One can read like a story that you can see how this things about. So this is another asymmetric wake around the round jet. So it not necessarily for a particular similar geometry you can have symmetric wake. So this may not be the situation, because Reynolds number decreases with the spatial location. So obviously turbulent die out. So when turbulent dies out, it's going to delaminarize the system. So and that is one of the reason you can think about why in the cricket fraternity, the ball they actually try to rub. What they want to do, the one side they want to always keep it shining, okay. The other side they want to keep it rough, and by doing that, they are trying to make one side more turbulent. So what it does, one side you become basically this flow separation. So what it does exactly, the asymmetric wake which creates when the bowler bowls. So the asymmetric wake actually creates a different kind of drag. Obviously lift come from the rotation, so different kind of drag. So that's why the ball swings actually. So there's a classical example where you have this asymmetric round wake when you have this kind of show. Now again, if you have a wall bounded, so this is kind of a confined flow. So wall bounded flow where you can do the scaling, and these are if somebody takes and boundary layer theory and all these things, so that you get a different law of the wall. You get inner layer, you get outer layer, and there is a overlap region. So these are, you look at any turbulent flow book or boundary layer theories or the FM height of the viscous flow. So this is the picture where you see the different region and how these different regions are going to be there. So these are the, now as I said, the wall roughness. So wall roughness also can change the turbulence nature. So obviously when you have the different kind of roughness, it's going to change the scaling law. What I have shown the scaling law, that is also very much true for when you have the smooth wall. Now, cricket ball is a classic example where you make one side rough and another side is this thing. So obviously in the rough wall also you can have scaling law. So this kind of roughness, this have been kind of, this is the focus of study. People have been studying. So you can again do order of magnitude analysis. And this particular picture shows how the friction factor changes, whether you have fully rough to fully smooth. And if you do the scaling over that, then you can bring in this hydraulically smooth or hydraulically rough. So I'll come to the scaling law completely. So these are some of the correlations. So, and then, so this is how you get the U plus, which is connected with your constant and things like that. If you rough zone, so there would be friction factor, what you can estimate here. So idea here is that you try to see effect of this roughness and how much roughness can create an extra bit of turbulence and how they are going to be affecting the system. Okay, so obviously this brings down to the turbulent boundary layer, and the turbulent boundary layer you will have the different kind of region. Now the same boundary layer, if it is on the rough surface, then it's going to showcase different kind of regime of the tower. So this is what the boundary layer definition, when you know that when the free stream velocity, I mean the velocity profile reaches the 99% of the free stream velocity, so you get the boundary layer thickness and you get the momentum thickness. So this you can estimate, and this is the scaling law that you get. So you have a viscous sublayer, you have buffer layer, and then you have the log layer. So whenever, I mean, why they are important? Because you will see when you go to the turbulence modeling, because resolving the boundary layer or the wall layer is very, very important, and how we resolve well, that can dictate a lot of the other phenomena of the physics. And that is why these laws are going to be important. And most of the RANS-based turbulence model, they use this kind of laws and the law of the wall. Now, this is what I have already talked about, the wall bounded shear flows. So you see the turbulent boundary layer, the pipe flow, and wall roughness. So you have essentially different regions. So one would be close to the wall, then there would be intermediate or overlapping region, then it would be outer layer. And the velocity profile, they are going to behave in these three different regions differently. So that is the idea here. So, and if you should have that scaling so that you can. Now, kinetic energy of the, okay, I can start from here. Is there any question? So maybe I'll stop, and then in the next session, I will continue from here. Anybody has any question? Yeah, you can type in the chat box or raise your hand. Yeah, Sasikant, you can talk, unmute yourself.
Hello.
Yeah.
I'm audible, sir?
Yeah, you're perfectly audible.
Okay, yes. So my question is related to the characteristic length scales which we choose for the vortices. For example, if we have a flow in a pipe, isn't it possible that the vortice is formed in such a way that it is of the shape of ellipse? So if it is an ellipse, then the characteristic length scale is the major axis or minor axis?
Okay, so that, okay, there are two aspects of the question if you have understood correctly. So only elliptical size of the large scale structure is possible if your surface area of that particular pipe is going to be elliptical, right?
It is a normal, like a simple D diameter pipe.
So if you have a uniform D diameter pipe, and there is no possibility of getting a structure like an elliptical at the initial stage. Initial stage, the large scale AD size will be of the circular. I mean, the characteristics length would be of the order of that pipe only.
Yes, but if we increase, like go to high Reynolds, like very high Reynolds number, by
even if you go to high Reynolds number, the characteristics length would be order of that D only. It cannot produce any elliptical shape ADs.
Okay, like means it is not possible.
No, it is not possible, because this is a very much geometry dependent property. So whatever your geometry, the large scale structure of the AD would be of that size, that length.
Okay.
That would be the characteristics length. And but when it transport through and its smaller ADs are formed, that time it can take that shape due to this vortex staging and the vortex rotations, and that is possible. But at the beginning, it cannot take that shape.
Okay, sir. Okay. And sir, this stretching is like every time only stretching is responsible for energy cascades. Like, is there any other?
Mostly stretching is responsible for that stretching and rotation. But whenever you go to this temperature dependent situation like reacting flows, the barocooling term also comes into the picture.
Okay. Like for majorly it is stretching.
Yes, because stretching also involves some sort of a rotation also, that term.
Yes. And sir, for example, sometime in the simulations, for example, if we are simulating some turbulent flows, generally people go with the RANS study, like steady RANS. So is it like how much it is a good approach to solve a turbulent?
Yeah.
have
So
no problem using RANs.
question is very, I mean, it's a very good one, but it's also generic one, because whether the steady RANs is applicable or not, that would be dependent on the particular flow of interest, what you are solving. Let's say if I take a simple example of flow over I mean, obviously high Reynolds number flow over a cylinder,
Yes,
it
sir.
is invariably statistically unstable because your vortex setting pattern is always remain like that. So
Yes,
there,
yes,
if you
definitely.
use steady RANs, it is absolutely wrong.
Okay, okay. And if we have flow something like swirling flows,
Swelling flow also absolutely wrong.
okay,
If
we
there
should
are
never.
situations where the flow is statistically stationary, then only steady RANs might give you, but it is going to give you only mean flow properties. It's not going to give you information about, anyway, any RANs equations I have shown you, they are only solving for mean flow properties.
Yes, 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 yes. So like
Okay,
it is.
so yeah, I'll show that when I come in the next session, showing that I mean, I showed you that energy diagram, which is also visible here. When you do this different modeling, which model does what? I think that will also clarify more. Which model does what?
Yes, yes, yes. Okay, miss, if I see like in a concluding remark, like we should not
Yeah,
go
so,
with the steady RANs for the swirling flows as well.
yeah.
Okay, 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 sir. Okay, sir. Thank you, sir.
Any other questions?
Yeah, thank you, sir.
Yeah. Okay, so then we'll wind up the session, and then we'll rejoin back a couple hours time. Then I'll take it up from here.